Welcome to Week 7, Lecture 2, Correlation Continued. In the last lecture, we learned about correlation. We also learned how we could use the Pearson R concurrent with hypothesis testing. Before we go into more detail, however, there are a few things we need to discuss in terms of understanding and interpreting the Pearson correlations. More specifically, to understand and interpret the Pearson correlation, we must first understand common errors involved with correlations. A correlation simply describes a relationship between two variables. It does not explain why two variables are related. A correlation should not and cannot be interpreted as proof of a cause and effect relationship between two variables. A common error is to conclude that correlation implies causation. Correlation and causation. One of the most common errors in interpreting correlation is to assume that a correlation necessarily implies a cause and effect relationship between two variables. Although there may be a cause and effect relationship, the simple existence of a correlation does not prove it. For example, suppose we selected a variety of different cities and towns throughout the United States and measured the number of serious crimes, our Y variable, and the number of churches for each of the towns. The data is presented right here. So I just want to point out that on the x-axis we've plotted the number of churches, and on the y-axis we've plotted the number of serious crimes. Note that the scatter plot shows a strong positive correlation. Thus, as the x variables increase, you'll find an increase in the y variables. More specifically, as the number of churches increase, you find that you have more serious crimes in a particular city. Does this relationship mean that churches cause crime? Does it mean that crime causes the creation of more churches? It should be clear that the answer to both is no. Although there is a strong correlation between churches and crime, the real cause of this relationship, in other words, the underlying variable that is driving this relationship that we have not measured, is the size of the population. In larger cities, what you'll find is that you have more crime and you also have more churches. Both occur because we have more individuals to attend churches and also more individuals to possibly commit more serious crimes. So this is a very good example of how a strong positive correlation, or in another example possibly a negative correlation, can exist, but it does not necessarily mean that that relationship is a causal relationship. So very important, correlation does not mean causation. Correlation and restricted range. The value of a correlation can be affected greatly by the range of scores represented in the data. Whenever a correlation is computed from scores that do not represent the full range of possible values, you should be cautious in interpreting the correlation. The correlation within a restricted range could be completely different from the correlation that would be obtained from a full range of scores. For example, in this figure, what we see is a strong positive correlation. So again, you're seeing a nice linear relationship here. It's pretty strong because you can just with your eye see the line there. And it's also positive as at the bottom, as the x score increases, the y score also increases. Now, if we consider the entire range, we would conclude that there's a strong positive correlation. However, if this relationship can be obscured when the data is limited to a restricted range. For example, if we were only to look at the data to the right of this dotted line here, we would get a completely different interpretation. In other words, if we were just to look at this data here and just ignore all the other data on the left side of the dotted line, what we would see is that there's really no relationship or at least that would be what we would conclude, that there's no relationship between these variables, when in reality, if you look at the full range of scores, there is a true relationship. In the same vein, if you take a look at this scatter plot, you would see that there's no consistent relationship between the x and the y variables for the full range of scores. Again, if we restricted the scores and we only looked to the scores that are to the right of the dotted line, what we find is that with a range of x values that is restricted, the data shows a strong positive correlation. So if we were to look at this simple restricted range, what we would conclude is that there is a strong positive correlation. But in reality, if we looked at the full range of scores, we'd realize that there is no relationship between the x and y variable. Therefore, it's very important that your data is not restricted. One or two extreme data points, often called outliers, can have a dramatic effect on the value of a correlation. With data based on averages, another error can arise. Averages suppress individual variation and may inflate the correlation coefficient. An outlier is an individual with an x or a y value that are substantially different from the values obtained from other individuals in the dataset. The data point of a single outlier can have a dramatic influence on the value obtained for the correlation. In this example, we have a data set with 5 data points from which a correlation between the x and y variable is nearly 0. Actually, if we look at this graph right here, we could see that there isn't a very strong relationship between these values, and our correlation coefficient would be a negative 0.08. So it's very close to 0, indicating that there is no real relationship here. However, including one extreme data point, so we include a data point of 14 and 12, and here it is drawn up here at the end of this, including this extreme data point can strongly affect the data. So when you look at the data set overall, you can note that one extreme data point has been added to the original data set, and when this outlier is included in the analysis, a strong positive correlation now emerges. Our R has now gone up to 0.85, which is again a very strong correlation. So note that a single outlier can drastically alter the value of a correlation, thereby can affect one's interpretation of the relationship between the x and y variable. The problem of outliers is a good reason why you should always look at the scatter plot instead of simply basing your interpretation on the numerical values of the correlation. So in other words, it's very important for you to take a look at the outliers and determine if some values are extreme, they need to be removed before running your analyses. The next common error involving correlation that we're going to discuss is the property of linearity. If there's no linear correlation, that doesn't necessarily mean that no correlation exists. For example, if you look at this scatter plot, you would have a very difficult time finding a linear relationship among the x and the y variable. That doesn't necessarily mean that there isn't a relationship. It just means that the relationship is not linear. In this example, you have a function that's curved that is in terms of the relationship. That doesn't mean that this relationship doesn't exist. What it does mean is that it's not linear. Now, for the purpose of this course, we're only going to discuss linear relationships. But it's something for you to keep in mind in the future if you decide to continue doing statistics. It's just because you don't find a linear relationship that doesn't mean that a relationship among the variables do not exist. The final common error involved in correlation that we will discuss is the correlation and the strength of the relationship. A correlation measures the degree of relationship between two variables on a scale from 0 to 1. Although this number provides a measure of the degree of relationship, many researchers prefer to square the correlation and use the resulting value to measure the strength of the relationship. One of the common uses of correlations is for prediction. If two variables are correlated, you can use the value of one variable to predict the other. For example, as we mentioned in the last lecture, college Administration's office do not just guess on which applicants are likely to do well. They use other variables such as SAT scores, high school grades, etc. to predict which students are more likely to be successful. These predictions are based on correlations. By using correlations, the Administration's office expects to make more accurate predictions than would be expected to be obtained by chance. So, in general, a squared correlation, or R-squared, measures the gain in accuracy that is obtained from using the correlation for prediction. In other words, the square correlation measures the proportion of variability in the data that is explained by the relationship in X and Y. It is also sometimes called the coefficient of determination. The value of R squared, or the coefficient of determination, measures the proportion of variability in one variable that can be determined from the relationship with other variables. A correlation of R equals 0.8 means that R squared would be 0.64. In other words, we can say that 64% of the variability in the Y scores can be predicted from the relationship with X. For now, you simply should realize that when two variables are consistently related, it is possible to use one variable to predict the values of the second variable. Let me go ahead and go over some examples that might demonstrate this concept a little bit better. Let's start out by looking at data set A. Data set A shows the relationship between IQ and shoe size. So our our Y variable is IQ, as it's represented here on the vertical axis, and our X variable is shoe size, and it's represented here on the horizontal axis. This data set contains a correlation of R equals to 0. In other words, our R squared is 0. So, in other words, or another way to say it is, knowing a person's shoe size provides no information or 0 information about the person's IQ. So in this case, the two measurements are completely independent and there is no overlapping information between the two of them. So based on the way we worded things before, we can say that 0% of the variability in the IQ can be attributed to the relationship between IQ and shoe size. Now let's take a look at data set B. Dataset B is looking at college GPA and SAT scores. And if we look at this, we can see that there is a good positive correlation. And if we calculated our value for R, we'd get a value of 0.8. Between the relationship between college GPA and SAT scores. So, of course, we should be able to know what our R squared is because it's the example that we use. We get an R squared of 0.64. Students who score high on the SAT tend to have higher grades in college than students with low SAT scores. From this relationship, it is possible to predict a student's GPA based on his or her SAT scores. However, you should realize that this prediction is not perfect. Although some students with high SAT scores tend to have high GPAs, this is not always true. In terms of the way we worded things before, we could also say that 64% of the variability in a student's GPA is predicted by the student's SAT scores. Now, let's consider a different data. Finally, let's consider data set C. Data set C is looking at the relationship between monthly salary and annual salary. Now, just by thinking about that, your annual salary is composed of your monthly salary. So chances are one could easily predict the other. If we went ahead and did an R value for this, we would find that this shows a perfect linear relationship. In other words, R equals 1. So with an R equal to 1, we get an R squared of 0.1. In other words, we are at 100% predictability. Thus, if you know a person's monthly salary, you can predict perfectly the person's annual salary. In this case, there's complete overlap between the two measures because the person's monthly salary provides exact information as the person's annual salary. So another way we can word it is 100% of the variability in a person's annual salary is predicted by their monthly salary. It's now time to switch gears and start talking about hypothesis testing with the Pearson correlation. A sample correlation often is used to answer questions about the general population. Inferential statistics uses samples to draw inferences about the populations. In the past, we have been concerned primarily with the use of sample means as a basis for answering questions about population means. In this section, we will examine procedures for using sample correlations as a basis for testing hypotheses about the corresponding population. And to do so, we're going to conduct hypothesis testing using the 4 steps that we've done throughout this term. Step 1, the hypotheses. The basic question for this hypothesis test is whether or not a correlation exists in the population. The null hypothesis is no, there is no correlation in the population, or the population correlation is 0. The alternative hypothesis is yes, there is a real non-zero correlation in the population. Because the population correlation is traditionally represented by the Greek letter rho, the hypothesis testing will be stated in terms of that symbol. So let's go ahead and write it. Our null hypothesis is rho equals 0. In other words, there is no population correlation. The alternative hypothesis is rho is not equal to 0. In other words, there is a real correlation. The correlation from the sample data will be used to evaluate these hypotheses. However, you need to consider that there is always the possibility of sampling error. Specifically, you should always expect some error between the sample correlation and the population correlation it represents. One implication of this fact is that even when there is no correlation in the population, in other words, rho equals 0, you are still likely to obtain a non-zero value for the sample correlation. This is particularly true of small samples. Thus, the purpose of hypothesis testing is to decide between the following two alternatives. There is a non-zero sample correlation that is simply due to chance, or the non-zero sample correlation accurately represents a real non-zero correlation in the population. Step 2 of hypothesis testing is setting our criteria. Again, we need to select an alpha level, which is often given to us. Then next we need to find the degrees of freedom. The degrees of freedom for the correlation test is actually pretty straightforward. It is simply defined as n minus 2. So if we have a sample size of 10 individuals to compute our degrees of freedom, we simply take the value of n and subtract it, which gives us a degrees of freedom of 8. Then we just need to go to our table. In our insert or in the back of the book, we're going to be looking at table A6, which you will see over here for critical values for the Pearson correlation coefficient. Again, we have our alpha set at 0.05, and we have degrees of freedom set to 8. So our corresponding critical value is 7.07. Next, we go to step 3, computing our sample statistic. In other words, we compute our Pearson R, and because we covered this in the last lecture, I'm not going to go into detail here. Plus, we're going to have another example in the following lecture. And finally, the 4th step of hypothesis testing is making our decision. A researcher using a regular two-tailed test with an alpha of 0.01 to determine whether a non-zero correlation exists in the population. We have a sample of n individuals, and we have an alpha level set to 0.01. And so we just need to use the table to find the corresponding critical value. And so to do that, we first need to calculate our degrees of freedom, which is again n minus 2, and in this example, n is 30, so 30 minus 2 is 28. And we just need to go to our table, and we need to first find our corresponding n value, and then we need to go ahead and find our corresponding alpha level. In this example, we get a value of 0.463. So again, our critical value is 0.463. So the sample correlation must have a value greater than or equal to plus or minus 0.463 to reject the null and to conclude that there is a significant correlation in the population. So in other words, we compare our R obtained and see if it's greater than our R critical. Any sample with a correlation between the values of 0.463 and negative 0.463 is considered within the realm of sampling error. In other words, it's not significant. Directional hypothesis in the one-tailed test. For some reason, Traylor did not think including a two-tailed option for the critical values of the Pearson correlation coefficient was necessary, so I won't be asking you to use the directional test for correlations. But I do want you to know that it is possible to have a directional test for the Pearson correlation coefficient. We can use a directional test to determine whether or not there is a positive correlation in the population. So if we want to do that, we would just state our null and our alternative. And I like to, when I have a directional test, I'd like to state our alternative first because that's what we expect to happen. And so our alternative hypothesis is that there is a positive correlation. And the way we state that in terms of simples is simply rho is greater than 0. So in other words, the population is positive. Our alternative hypothesis is that there is no positive correlation. So there could be a negative correlation, but there is no positive correlation. So the way we state that in symbols is simply rho is less than or equal to 0.